So what should I talk about? I know that young people sitting here, you are already tired. It's already not the first day, a lot of different lectures. So I tried to make it not extremely scientifically, not no more formulas or something, just more that you will have overview. So, oops, is it working? Ah, it is working. So I am coming from Lithuania, and I will make a short introduction about Lithuania, because I hope that you do not know very well. So if we look at the map of Lithuania in 15th century, Moldova and Lithuania were neighboring countries. We had a joint border. You can see the borders of Lithuania and Moldavia is, oops, here, you see. And we had a joint border till Black Sea. But now Lithuania is much smaller. And as already President mentioned, I'm coming from roots, my roots are from Vilnius University. And Vilnius University was established in 1579 as a university. Before that, in 1570, it was Jesuit college. And from college, it progressed to the university. And the trick is that Jesuit college had a library, and this library was inherited and is going to Vilnius University. So funny thing that library of the university is 9 years older than university itself. So university have a lot of courts, and also please do not think that it's an ancient city and nothing well developed. Here you see on the upper right, lower right corner, the new National Center of Physics and Technology, where my labs are now located. And Vilnius also old city, but we have some new regions with some big buildings, a business center. And interesting thing, it's not Lithuanian propaganda. United Nations did the survey of happiest country for young people. And surprisingly, for me, very much surprisingly, it was world's happiest country for young people last year. So let's go to materials. Now the question, what is common between gramophone, Edison, ICE, the quick train in Germany, cameras, and skis? Do you know? Because you know, when I'm reading lectures, I usually ask a lot of questions to students. The answer is piezoelectrics, because piezoelectrics generate sound in gramophone or in patephone. In intercity express trains, active damping is made by piezoelectric lead zirconate titanate ceramics, so you can sit nicely, quietly without shaking. Also, piezoelectrics move the lenses and so on, motors. And skis, if you want to go down the slope very quickly, skis also have active piezoelectric damping. Some of them, not all of course. So these mechanisms, what I have not pictured here, also Hubble telescope also was the piezoelectric actuators to focus better the images. So we have already met piezoelectrics. So, but there are another materials. There are ferroelectrics. If you heat them, they generate charge. And the previous speaker spoke about Peltier elements, Seebeck effect, and so on, Peltier effect. But pyroelectrics, it's created charges by temperature. Another, piezoelectrics, that, for example, if you take quartz and hit it with hammer, you generate charge. And finally, it's ferroelectrics. Ferroelectrics, it's like battery on the lower right corner. And interesting thing that you can, applying external electric field, you can change the polarization. You can switch. And this appears after structural phase transition. So atoms in the lattice, they change their arrangement. And due to that, dipolar moments appears. So structural phase transition, you know, of course, the phase transitions from liquid to solid and to gas. Can you give me the example? Yes. Who thought that? Excellent. Water. In winter, we have solid. In summer, we have liquid. And if we boil it, it evaporates. So we have three states. But sometimes in solids, we have a different arrangement of atoms. And again, I refer to the previous lecture of colleague on materials. Coal, C. You can have diamond. It's one atom arrangement. You can have simple graphite, another, the same atoms, only differently arranged. And finally, you can have graphene. It's two-dimensional layers. And also was mentioned the carbon nanotubes, because you can, then you have a sheet of monoatomic layer, you can roll it, or you can make ball, C60, for example, and so on. So, and properties of these materials due to atom arrangements changes completely. So if we look at the materials, so we have dielectric materials like timber or glass. Then we have piezoelectric, pyroelectric, and finally, some of them, they are ferroelectric materials, which, as I mentioned, you can change the polarization by external electric field. So the best piezoelectric and best pyroelectrics are ferroelectrics. And they use, of course, you can make infrared cameras to measure the temperature of oceans from satellites. Before the coffee break, it was nice lecture on nano satellites. So from nano satellite, if you have infrared camera, you can measure the temperature very precisely. You can have for ships to see how deep is water and how many fishes are. So fishermen uses ultrasonic equipment. And also surface acoustic wave also are used for different applications in different fields. So ferroelectrics can be applied in many, many ways. So if we have bulk, you can use capacitors, generators, piezo motors, piezo actuators, electrorestrictive actuators, sensors. If you have films, which can be produced by CVD or PLD, that's another technique. So again, capacitance, sensors, in electronic schemes, and so on. And also you can use memory as a memory, and integrated optics and gratings, all different things. So let's see, for example, application of memories. As I told, you can have ferroelectric material, with external electric field, you can polarize up or down. And due to that, you can write information like bits, 0, 1, 0, 1, and this information can be read. So in Japan, the transport cards, they are using this ferroelectric memory. It's called Suica, and from Japan, Super Urban Intelligent Card. And Suica means watermelon from Japanese language. And it's contactless card. You put like bank cards now, you can pay very easily. So ferroelectric market is growing each year, and it's estimation that it will go over $2 billion in the future. And the companies there are the list: Fujitsu, Cypress, ROM, Texas Instruments, they do these memories. Another interesting material, each one of you have mobile phone, I guess. Now it's difficult to find anyone who do not have. Mobile phones use batteries. You must charge it. For this, you use ionic conductors. So ionic conductors, when you have a crystal lattice, but some ions can move inside the lattice. And due to that, you charge the battery, then you use it recharges. So another interesting and very useful material. Pyroelectricity, as I mentioned, is night vision, infrared vision, heat sensors, energy harvesting, and piezoelectricity as well. You can see if you press and extract, you generate charge. So the trick is that ferroelectric materials have a phase transition. What does it mean? And here is lead titanate or barium titanate perovskite material, and the titanium or zirconium is sitting in the center of the lattice, cubic lattice. But then you lower the temperature due to the interaction of atoms inside the unit cell. Energetically, is better for atom to move off-center position. So it shifts up or down. There are two equivalent positions. It's in red and white shown. And due to that, charges are not compensating, and you have polarization of the material. So as I told, you have up or down. And phase transitions are, as I mentioned, and lady told very correctly, liquid-solid, but its structure changes. And here in perovskites, for example, you have a displacer phase transition, then one atom moves. There are another class of materials which always have dipole moment inside. And this are disordered at high temperature, so total polarization is zero. When you cool down, it orders, and when ordered, you can switch polarization again, and these phase transitions are called order-disorder type phase transitions. So in high temperature phase, perovskites are centrosymmetric. It's B, like titanium or zirconium atom, now it's green, is in the center, is high temperature phase. Then you cool down, you get off-center positions, two equivalent positions, and it's ferroelectric phase. Now you can switch. Ferroelectric historically came from ferromagnetic materials, because ferro means iron, and the magnets usually have been with iron. So it was ferromagnetic, where the magnetic field you have and you can reorient. And this is ferroelectric, there you have dipole moment and you can reorient. So further on, ferromagnetic and ferroelectric materials. Also, there are some materials which have both magnetic moment and dipolar moment. In this case, we can talk about multiferroic. And multiferroic is interesting in that sense that with magnetic field, you can switch. In ideal multiferroic material, you can switch polarization. And with electric field, you can switch magnetization. So that's why it's called multiferroic material. So multi-source energy harvesting, one of the possible applications. Then you have solar energy. You can collect thermal energy. You can get also mechanical energy. And also for this type, the new, very emerging new class of materials, hybrid halide perovskites are coming into the market, and one company already is producing solar cells with halide perovskites. So as you see, it's a lot of applications, which I mentioned very briefly. And the future for you is one-dimensional nanostructures. So it can come to nanosensors, molecular electronics, biochips, and smart electronics in the next generation. So in medical, it's used for echoscopy of heart, for example, and here you can see a picture of my heart. That's ultrasonic measurements. And also, due to Doppler effect, you can see the direction of blood, which is coming in or going out. And this, with computer, you can color in different colors, and you see how your heart properly is working. Another application, I think maybe you are not driving yet, but parents have cars. So those who have diesel cars, it's the injection, fuel injection into the cylinders. It's also used piezoelectrics. Also, the same is used for inkjet printers. Another very important application is for nonlinear optics. Now everyone in the world is looking for fusion, and to get the fusion, you need a powerful lasers. And for powerful lasers, you need a second harmonic generation. When the light comes in and you have ferroelectric material, which is polarized up and down, it's like called PPL, periodically poled lithium niobate, for example. And due to that, effect is much stronger, and conversion to the second harmonic is much higher. And in the picture, you see how big ferroelectric crystals can be grown. The lady with one KTP crystal. So Ramtron is one of the leading companies in ferroelectric memories, and computing, automotive, meters, communications, all industrial applications, everywhere where you need electronics and memory, you can use ferroelectric memory. So similar picture what was shown with chemical vapor deposition. You can construct whole ferroelectric RAM memory, and then you can use practically everywhere. You can see in the picture. So another interesting thing with polarization, that's a Japanese company which is developing. It's called like piezo force microscopy. Then you have needle, you have ferroelectric layer, which is in blue, and you can write information. So you can write information such that in 50 nanometers, you can write a lot of bits up and down. So here you can see that in 50 nanometer scale, which is shown on the right-hand side, you can have around 10 terabyte per square inch. Inch is 2.5 centimeter roughly. And you can do a lot of things with that. So in future, commercially, I hope it will be available. So market size, ferroelectric market size is growing tremendously. It's in billions. Piezoelectric device market is even bigger because it's used in medical applications, in cars, everywhere. So it's $52 billion. So then you have a phase transition. You have especially displacive type phase transition. You have a soft mode. Each atom vibrates in the lattice. And this set of vibration give the vibration types, which is called modes. And then we have displacive phase transition. One of the modes is not stable, and its frequency goes to 0. This is called its soft mode. How to investigate these materials for applications? You need to have a dielectric spectroscopy because you need to know the properties of the material. So dielectric spectroscopy is a technique which characterizes electrical properties of materials at different frequencies. And this, if you want to use in telephone, you need to know at 1 gigahertz or so properties. If you use for radar or so, you need to know around 50 gigahertz, and so on. So in computers also, processors are frequencies increasing, so you need to know properties of material at such high frequencies. And the dielectric spectroscopy shows the response of material to external electric field. And this, the answer to external electric field, is called dielectric permittivity. So let's look at the electromagnetic spectra of electromagnetic waves. We have very low frequencies like DC. Then we can go to higher frequencies, radio frequencies. Then we go to up to 3 gigahertz, up to 100 gigahertz, it's microwaves. Higher than terahertz. Further on is infrared light. Then is short range of visible light, ultraviolet light, and then goes X-rays and gamma rays. And here below, it's where it's possible to apply, like cell phones, TV, radio, AC power, radio location, and so on. So to measure this, you need to use a set of different methods. And we in Vilnius, we have a broadband dielectric spectroscopy. So we are going from 10 to -5 hertz, but nobody measures so low frequencies because experiment takes too long time. What we reach 10 to -3 hertz. And it took a week to measure. And further on, you go to coaxial lines, vector network analyzers, then it goes time domain spectroscopy or terahertz spectroscopy, and Fourier transformed infrared spectroscopy. And it's combined with X-rays, EPR, NMR, and ultrasonic spectroscopy. You can get the whole information about the material. So here is the example of vector network analyzer with coaxial line at the end where you can measure the properties. Here different waveguide systems, which you put the sample into waveguide and measure the properties of the material. And here is the 180 to 120 gigahertz setup, which measure in 6-port method. And of course, you can measure not only reflection, you can measure reflection and transmission and get all the material parameters. For example, this setup, the ring method, is to measure ferrite magnetic susceptibility. As a dielectric permittivity we have also magnetic susceptibility. And with this, we can measure magnetic susceptibility of a material. This project was very important for CERN. And we still have a project with CERN to measure at high frequencies magnetic susceptibility, because not many labs in the world can do that. And to direct the protons, you need to have also magnetic field. And because pulses are short, so they need to know the magnetic susceptibility at high frequencies. And that's an example. That's colors. The red is the strongest electric field, how the mode or electromagnetic wave propagates in rectangular waveguide. Further on, now you know that already, I think in Los Angeles, there are cars, taxis without drivers, autonomous cars. So how car will know where to go? To know is a tree on the road or another car is standing, they need radio location. And radio location, there are antennas in the car, and these antennas emit 75 gigahertz frequency. And then they register reflections, and from that computer calculates how far is the object. So with this, we had a project with Honda, helping them to measure the properties of plastic, which are used for bumpers, because it's on the bumpers usually locators are located. And this we need to have very low dielectric losses. If it have big dielectric losses, the signal will not get through. So in our lab, we also have not only microwave, but also PLD machine to make thin films, and EPR machine, electron paramagnetic resonance. So PLD is already, as colleague told, you can construct like Lego, like cake with different layers, atomic layers with high precision. It's expensive, but the idea to make it from magnetic and ferroelectric material, multiferroic, which can be used both with magnetic and electric fields. So totally, our group had a lot of projects, talks at the conferences, papers, and so on. Partners, it's a lot of universities, which I will not talk. The last interesting thing, which I will not get into very details, it's van der Waals ferroelectrics. So like graphene, you can split from actually, when you write with pencil on paper, you leave the trace of graphene, actually monolayer. And there are ferroelectrics with van der Waals bondings, which you also can split and have very thin layers, monolayers, one atomic layer of the material. So, and here is our building as it was a couple of days ago. So if you decide and you like solid state physics, we are looking for clever students. And to give a few formulas at the end, and thank you for your attention, and feel free to ask.